Basic hyperspectral analysis. In this tutorial, we will analyze spectral profiles from obvious reflectance data, compare image spectra to known library spectra, extract mean image spectra from regions of interest, and design color images to discriminate mineralogy. In this exercise, we will analyze spectral profiles of pixels within a reflectance image, then compare them to library spectra of known materials. Hyperspectral data analysis commonly involves apparent reflectance data where the imagery may have variation in illumination due to topography. With reflectance data, pixel values typically range from 0 to 1 but are often scaled by some factor to yield integer data. The apparent surface reflectance image we will view next has been scaled by 10,000. Click the Open button in the toolbar. Select the image file and click Open. Out of 224 bands of this average scene, ENVI automatically determines the best band to approximate a true color display. In this case, it assigns band 29 to red, 20 to green, and 12 to blue. This band combination does not offer a good color contrast among the different materials within the scene. Click the Data Manager button in the toolbar. Scroll through the list of bands in the image and select band 183, band 193, and band 207. Click the Load Data button in the Data Manager. The resulting band combination provides a better color contrast throughout the scene. ENVI can extract horizontal, vertical, and spectral profiles from any image display. Hyperspectral data analysis is primarily concerned with extracting spectral profiles, which takes spectral information from the whole file and not just the bands displayed on the screen. In the Layer Manager, right-click on the new image display and select Profiles and Spectral Profile. Within the image is a small white dot surrounded by 4 white corners. The dot represents the selected pixel and the spectral profile shows the spectrum for that pixel. Note the shape of the reflectance curve in the spectral profile window. The gaps indicate the bad bands marked as band in the ENVI header file. These are primarily water vapor bands that would have caused spikes in the reflectance curve. Click the Show arrow on the right side of the spectral profile. A plot key appears with the spectrum name and pixel location. You can also use this panel to set the plot properties. Click the Remove All button above the plot key to clear the spectral profile. In the Go To field on the ENVI toolbar, type pixel coordinates 325, 444, and press the Enter key. The display centers over a pink area in the lower part of the image. The spectral profile updates with the spectrum of that pixel location. This spectrum represents an unknown material. Spectral libraries are stored in ENVI spectral library format, with each line of the image corresponding to an individual spectrum and each sample corresponding to an individual spectral measurement at a specific wavelength. From the menu bar, select Display and Spectral Library Viewer. On the left side of the Spectral Library Viewer, expand the IGCP 264 folder and expand the IGCP_1 collection. Click on the kaolinite KL500 spectrum and note the shape and detail of the reflectance curve. Also note how the X and Y units of the spectral profile plot are scaled differently from those of the image spectral in the spectral profile. Click the Show button in the Spectral Library Viewer to see the plot key for the kaolinite spectrum that you selected. Select the kaolinite KL500 spectrum name from the plot key of the Spectral Library Viewer and drag it to the Spectral Profile dialog. The Spectral Profile automatically scales the y-axis to accommodate the two spectra for direct comparison. Select the kaolinite KL500 spectrum in the plot key of the Spectral Profile and select the Curve tab. Change its color to blue. Continuum removal is a powerful visualization tool for spectral analysis. especially for absorption features. It normalizes the spectral signature so that you can compare individual absorption features from a common baseline. Select the Y data value drop-down list and select Continuum Removed. Zoom into the wavelength range of 2000 to 2500 nanometers. The double absorption features near 2200 nanometers offers a good reference point for comparing image spectra to library spectra. In this example, the shape of the reflectance curve of the mineral kaolinite closely matches that of the image spectrum. You can use ROIs to extract statistics and average spectra from groups of pixels. You can define as many ROIs as desired in a displayed image. In this exercise, we will view ROIs of known mineral types and extract mean spectra from the ROIs. Click the Region of Interest tool button in the toolbar. From the ROI tool menu bar, select File and Open. Select the XML file and click Open. This ROI file represents pixels where specific minerals are known to occur. In the Select Base ROI Visualization Layer dialog, select your image and click OK. The ROIs for each mineral type are listed in the Layer Manager. Right-click on any ROI in the Layer Manager and select Statistics. An ROI Statistics Results dialog appears with an embedded plot window that shows mean spectrum, first standard deviation above and below the mean spectrum, minimum and maximum envelope containing all of the spectra in the ROI. Close the ROI Statistics Results dialog. Right-click on the Region of Interest folder in the Layer Manager and select Statistics for all regions. The plot window shows the mean spectra for all ROIs. Zoom into the wavelength range of 2000 to 2500 nanometers. Compare the spectral features of each spectrum and note unique characteristics that might allow mineral identification. In this exercise, we will design color images to help discriminate minerals. Right-click on your image in the Layer Manager and select Profiles and Spectral Profile. Click the Select button in the ENVI toolbar. Click inside of the red ROI that represents kaolinite in the lower center part of the image. The spectral profile shows the spectrum for that pixel location. Right-click inside the spectral profile and select RGB bars. Red, green, and blue vertical bars appear inside of the plot to show the wavelengths assigned to each channel. You can click and drag the colored bars to change them to other bands. This is a good way to enhance specific minerals by centering one bar in an absorption feature and the other two on opposite shoulders of the feature. Zoom into the wavelength range of 2000 to 2500 nanometers. Disable the Region of Interest layer in the Layer Manager to hide the ROIs. Click and drag the red, green, and blue bars to the location shown in the figure. Right-click in the spectral profile and select Load New Band Combination. Because the green channel falls within the absorption feature, green values will be low. The red and blue channels have a higher and nearly equal reflectance, resulting in a purple display in areas where kaolinite is abundant. Experiment with other pixel locations using the mineral ROIs as a guideline to highlight those features with new color combinations. You should begin to understand how the RGB colors correspond to the spectral signature. You can also predict how certain spectra will look given a particular pixel's color and the RGB image. Then you can design and test specific RGB band selections that maximize your ability to map certain minerals. This is a crude way to discriminating mineralogy based on different color composites. Thank you for watching.